My name is Alex Kalinowski. I am assistant professor of AI at Empire State University, which is SUNY's online arm. And we are developing their programs at the bachelor's and master's level in data science. And my talk today is going to be on why large language models, or LLMs, need ontologies as their backbone. So this is going to be a little more AI focused with some of the mechanics of how these AI models, specifically large language models, actually work. So what's in their guts, and how can we use those guts to actually understand what they're doing and ground them in the real world. So I'm going to start with two statements: Jake with the assist and Voracek with the goal. So if I asked you to rate these two sentences on a scale of 0 to 5, 0 being not similar, 5 being very similar, any guesses as to how similar these two sentences would be? 3? Fair enough. What's your rationale there?
Two words are in the same position with the same word, so.
The with the? Yeah. Right. But semantically, those are just kind of fluff tokens, if you would, right? So how about these two? Jakub nets the penalty shot, and Jake picks up the helper. 0. All right.
I'm going 4.
4. All right. I like 4 better. And I'll show you why. Same player, 2 different sentences, or really 4 different sentences. So this is Jake Voracek of the Philadelphia Flyers. And I love this photo because he's scoring a penalty shot on Marc-Andre Fleury, the goalie for the Penguins, our hated rival. And what we're getting at here is the difference between surface form, which, as you pointed out, the with the in both sentences, that's a surface form, versus semantics. So the surface wording is what we actually call tokens in large language modeling. Those surface wordings can differ, but the meaning of these sentences actually overlaps. And this is the entire linguistic field of semantics. These large language models see tokens as their training. So while I love the Philadelphia Flyers, I actually pulled this example from a benchmark data set called the STS, or Sentence Textual Similarity Benchmark. And the two sentences in this benchmark, Jake with the goal and Voracek with the assist, are actually semantically ranked very low when compared to each other. So we're missing here a ton of context, and if we're fine-tuning a large language model using that information, we're just feeding it bad data. So then, are these semantics lost when we use these large language models? And if they are, how can we inject them back? So some of the other pain points in using LLMs: entity identity, right? Here, Jake, that's mentioned in the sentences, is the same as Jakub Voracek. So same person, different names. Same thing with types and roles. Is it a player? Is it a team? Is it potentially a city? What kind of thing is this token? And we'll keep hitting on this point of strings versus things. Same thing with relations. Assist and goal link the player to the event. So scoring a point or getting a point on your stat line in hockey. And plenty of other things too. Constraints. Person can only have one birthday. The time. A player can switch teams over the course of a season or in between seasons, as well as things like hierarchies. So a woodpecker is a bird, which is an animal. So this highlights the need to factually ground these LLMs, because all they're seeing is these tokens, and while they're trained on these contextual windows, if they don't actually know or are grounded in the real world, how can we expect anything meaningful out of them? So how do we go about grounding LLMs? Well, first, I'll talk about AI more in general. So there's two different camps within AI. There's symbolic AI and connectionist AI. And in symbolic AI, the idea here is don't mimic how the human brain works, just try to use symbols or programs to encode everything that we possibly know. So a lot of different projects in this space. Really, this is work that's done in AI up to the 70s. Other projects then continued on in like the mid-late 90s. CYC is a big one where they just simply tried to write down everything possible. And it's a fool's errand. Versus connectionist AI, or sub-symbolic, where AI tries to mimic the human brain. And this is the entire field of neural networks and deep learning. And the first of those models was the perceptron model. And this actually came out in the late 1950s, but was not really used because we didn't have the compute nor the data to make that thing work. So neural networks were abandoned. There was a famous book in 1969 mathematically proving that the perceptron model had its limitations and couldn't scale. Well, all of a sudden, we get the internet, we get more data, we get GPUs. Now these things are a reality, and we interact with them on a daily basis. So how do we start to reconcile these two approaches? We see that these LLMs fall in the connectionist camp. How can we start to interject some symbolic AI to help them stay sane? So as any good computer scientist would do, we'll write down a set of requirements. So what are they requiring? Yeah, go ahead.
Kind of a side question, but why is that it's not going to scale well in the perception model?
Really because the perceptron is a linear model. At the end of the day, if you look at the XOR problem, exclusive OR, it can't differentiate between two classes. So if you have X and X and Y, you can't draw a line to distinguish between them. So further neural networks add things like nonlinearities to capture that, or add tons more parameters that were just computationally inefficient back in the 70s. So back to our requirements. Like I mentioned before, we need a way to translate strings into things. And we need a way of imposing constraints on LLMs. What are you allowed to output? So if we ask for a city and it gives us a date, clearly wrong. We also need to model the relationships between certain entities, because we wouldn't want those relational constraints to be invalidated either. So we really want a model for concepts, categories, and their subsumption hierarchies. So what I'm going to do is introduce ontologies and knowledge graphs. So anybody heard of an ontology before? No hands. Oh, okay. Usually no hands go up. How about a knowledge graph? All right, so some familiarity. So I'll give a soft definition for ontologies. An ontology is a formal and explicit specification of a shared set of concepts, really, and the relationships that can exist between those concepts. And typically, ontologies are developed to serve a certain domain. So I've worked in industry, worked at a large bank. We had an ontology that described our customers and the relationships between them, which accounts they had, things like that. And this was heavily used in those symbolic approaches that I discussed before. So if we go back to the example of hockey, a quick ontology that we could develop, in no means complete, we could have a list of core classes: the player, the position, the team, the game, their particular stat line. We have constraints. Any game has to have two teams, one of them being the home team, one being the away team. unless you're playing in the Winter Classic and you're playing outside. Stat line has to have a scope. Is it for a particular game or a particular season? And then we define the key relations. So player plays for team. A team has a player in a season, and that defines their roster. A player played in a game. So a lot of these seem pretty obvious in the way that we talk and share language. But the problem is, how do you translate that to something machine readable? So a knowledge graph is really just a materialization or a realization of an ontology. So if we have our ontology as this backbone and we start to feed in data, so specifics, which player, which game, which team, that's that materialization. So a knowledge graph really is just this network of things and the relationships between them. So it can actually materialize some of that data about Jake Voracek. And I know this is hard to read, and that's intentional, that it's kind of chaotic. So we can see the player Jake Voracek has an alias Jake, played in this particular game, scored this many points. We can add timestamps to these things. So we're really tracking all of those different variables and variances in a very structured format. And I say that this is chaotic, but it's nowhere close to actual knowledge graphs. So this is a visualization of the Freebase knowledge graph. This is one of the big open knowledge graphs that was available, isn't so really recent anymore, isn't super well maintained, but actually serves as a good test bed for a few different AI methods. I'll give the formal definition of a knowledge graph because it's going to be important later. And a knowledge graph is a tuple of three things. We have our entities E, our predicates or relationships P, and a set T of triples. So we're really linking two entities by one of these predicates. And those triples are going to be important as well. Knowledge graphs are multi-graphs in that they permit different parallel predicates between entities. So you could be born in a city, and you could also currently reside in that same city. So two different relationships between yourself and the city. So let's talk a little bit about large language models and knowledge graph synergies, how they can feed off of one another. LLMs help bring language, while knowledge graphs bring structure to that language. So this is a snapshot from a proposed framework back in 2024, which is still fairly recent, although at the rate that AI research goes today, that's ancient. But we see this synergized model in the middle, where the LLM provides this general knowledge, language probabilities that really underlie the structure of those LLMs, whereas knowledge graphs bring this domain-specific structure and knowledge. And it's done in a very explicit way. So one of the synergies that we get when we bring these together is the ability to explain why an LLM made a decision or make sure that an LLM makes a better decision. So we have a few different integration patterns that drive towards meeting those requirements. We can do a lookup at inference. So we write a prompt, feed it to an LLM. The LLM on the back end can later then check, is my output adhering to the knowledge in the knowledge graph? So think of this as phone a friend. We can do grounded prompting. So inject a few knowledge graphs triples, maybe where the tokens match, into a prompt as additional context. And I'll show a demo of that towards the end. We can do constrained decoding, so prevent impossible outcomes. So don't return two capitals for a particular state. Helps with the air quote hallucination problem. We can develop adapters and aligners, and that's really where I'm going to spend some time. And then we can do training blends too. So as you train the LLM, you feed in these knowledge graph triples as a separate data input source and try to jointly learn two different representations. So we're really going to focus on how to map LLM embeddings to knowledge graph embeddings so that things that are nearby mean that they're semantically similar. So the prior talk towards the end, they mentioned vectors and vector databases. We're going to see a lot of that here, although in a more mathematically heavy notation. So I'm going to talk about this adapter and aligner, and we're going to talk about aligning embedding spaces, which might not make any sense right now, but hopefully I can clarify. So who has worked with or trained their own large language model? No one. All right, finally got one. All right, maybe one. Yeah, even fine-tuning, right? So if you're building one of these models, you're probably working in a framework like PyTorch. It's giving you all of these different Lego blocks that you can put together to build a different model. And you run your data through that, you do backpropagation, you do that ad nauseum until your loss is small enough, and then you call it quits. In each of those building blocks are these different layers of your neural network. And each of those layers is actually what we call an embedding. So typically, these embeddings are Euclidean spaces, Rn, Rm, where m is going to be magnitude smaller than our entire data set. So if you think of the number of tokens in the entire English language, it's going to be huge. Let's compress that down into some embedding space of dimension, say, 768. So we're shrinking our information down, we're compressing it as a bunch of floating point numbers. So each of those rows will correspond to a token, and each column is your guess as to what it actually represents. But that's what the large language model learned during its training. Yeah.
I see that most people with the activations and embeddings are a little confused between the difference between activations and embeddings. So could you explain that?
The activation will be like what's getting fired. So basically think of it as an on-off switch. And that defines the different connections that go through the neural network. The embeddings are these giant matrices. So really what they're encoding is the relationship between this activation or this neuron here to the next activation or neuron. So what we end up with is these huge matrix multiplications to move our way through the network. And that's why GPUs are so expensive and readily used in training these models. So basically what I just explained, again, these LLMs are composed of neural layers. All of them convert this raw text into a low-dimensional vector of numbers. These vectors are the embeddings. And what's cool about these vectors is that even though if we didn't feed in any prior semantic knowledge, it kind of starts to learn it. So it learns this embedding space such that shapes and relationships between tokens start to arise. So the canonical example is the analogy man is to woman as king is to queen. Well, if we take the vectors for those four, they kind of form this parallelogram. So we're able to use vector math, or measure of the cosine angle between these vectors, to measure similarity between things. We can also do this same type of neural network, use this same type of neural network, and apply it to a knowledge graph. So a knowledge graph embedding, rather than focusing on the tokens, represents the entities in the graph as one embedding space and the relationships in the graph as another embedding space. And then we feed this to some scoring function, and the same idea here holds. Entities that are similar in nature should have vectors that are very similar, so that when we do computations, like measure the angle between them, that angle should be really low, means they're highly similar, versus if they're in orthogonal directions, that measure is going to be really high. They're dissimilar. In these methods, the entities and predicates are represented as separate objects, so we're going to need some fancy machinery to represent triples. So the triples here are really what contain that semantic knowledge, and we can think of the triples in a knowledge graph as sort of this canonical representation of an English sentence. So the tools that we have so far. We've got a set of natural language sentences. We have tons of different ways to state the same exact information. We have an ontology or knowledge graph that covers the same domain of those sentences. We use an LLM to generate embeddings. We use a knowledge graph embedding model to generate embeddings. The question is then, how do we merge those two together? How do we align them in such a way that we can take advantage of those synergies?
Yeah, how do you manage a conflict between your natural language model and your KDE?
We're going to see how we align the embeddings, and that essentially allows us to lock those things in together so that they're a little bit closer together. Hopefully that answers the question. So one of the ways that we can start to do this alignment is actually came from the 17th century. So the French mathematician Monge posed this question: how do we take a pile of dirt and fill in a hole in the laziest way possible? And that's really what we want to do. We want to take these two things that are different and align them in the cheapest way. Another analogy, right? We have two bowls of marbles, sentences and triples, and we want to minimize the effort of rearranging those two bowls to find best matches. And this is where the mathematical machinery of optimal transport comes into play. So optimal transport is the mechanism we're going to use to pair sentence clusters or sentences with triples so that they line up together and can lock in. This is what that does pictorially. What we're really doing is measuring the inner distance in each space. So we define a huge distance matrix of all the embeddings in each embedding space. And then we try to minimize the distances between those spaces as well. But the problem is that optimal transport can be really expensive to compute. These embedding spaces are really large. Measuring pairwise similarities between huge embedding spaces is also really costly. What if we did this on smaller batches? So we take a sample from each space and sort of use that to guide our later choices. And this is the idea of using this mutual information between the two, the joint probabilities, to finalize this optimal transport plan. So we can do it in a smaller way, and we can use that information and carry it forward to then develop better and better maps. Since it's fast, we can then add this into LLM training as well, better retrieval, fewer hallucinations. And just to show that this method works, we compared that work to the closest other model, and our precision is 98.6 versus one's hovering around 90. So the takeaway is that we can click these languages and graphs together such that meaning can easily transfer between the two. And that mechanism that we use to click them is optimal transport, and the other methods that we introduce to actually make that feasible. So there's one other lacking component, and this is, as I mentioned before, how do we convert these two different spaces that are learned in a knowledge graph embedding, the entity representations and the predicate representations? We really want a representation of the entire triple, because that's going to be the closest thing to a sentence. So we need one more tool to make this work. So like I just said, we could do a simple aggregation. We could take the entities, jam the vector with the predicate, and jam on another entity vector. But most of the aggregations that are proposed in the literature really only use the entities. So you're losing out on the important predicate information, that relationship between the entities. And since we have different parallel predicates, right? You can live in a city and be born in that same city. You lose that relational data. So we need to treat these knowledge graph triples as first-class objects, not just the entities and the predicates separately. So this is an example, another one of when this aggregation fails. We have David Lynch. He's an actor in and director of Twin Peaks. If we simply just take the entities A and B, concatenate them together, we lose all that predicate information. So we want to actually keep that. And what we proposed is a new neural network architecture, pairwise triple similarity scoring, that actually accomplishes this. So you see, we feed in our knowledge graph, we do some sampling, we do composition of the entities and the predicates, we push them through the network, we give it a score, we push that score back through the network and back propagate that information. And what we end up with are triple embeddings, which is what we wanted. And this does way, way, way better than the comparable methods. So ours is with the PTSS post-processing versus without it. So the takeaway is when these triples include that relational information and can be grouped together by that relational information, a simple model can recover those labels, which actually helps improve LLM recall. Is there a question?
How do you actually input that to the...
Yeah, so imagine, say you have a knowledge graph of 10 entities and 4 relationships between them. You have an index, 0 through 9 for those 10 entities, and a similar index for the predicates. And you're just feeding in, say, index 1 for the entity, index 3 for the predicate, index 4 for another entity. And that numerical encoding is then fed into this system, and that then triggers these different activations to kick off. We then do all this matrix multiplication. We have some score that comes out of the model at the end. We have a ground truth score. We compare the two. That's what's called our loss. We push that back through the model and update all those layers until we get something that we're happy with.
And that goes with the text that are also...
Same thing happens with text. So we take sentences and you actually take a contextual window. So say we have the sentence, the bank of the river, and you're trying to predict that last word, river. So you feed in the indices of all the tokens, and you're trying to predict the right index of the next token.
And so if I've already got a substantial token score from a well-defined ontology, the rule should be just drop A and B, and then that existing ontology, all those rules in the ontology should be reflected.
Yep. And then what we can do further is feed it to some encoding neural network, so that then we can align it better with an LLM. Excuse me.
Now, one of the places that I deal with issues with AI a lot is in medical language and moving things in and out of structured data formats where you have a little bit of a conflict between the natural language that the base LLM was trained on versus,
That domain specific, right? And that's where this really comes into play. You can take this general language model, you know, whatever it might be, BERT or whatever, pull down the pre-trained model, but you're feeding very domain-specific language to it, so it has no clue. So taking your ontology that describes that domain, embedding it, encoding it, and then using that as an additional input to that LLM helps to rectify the difference between those two things.
and then you have the OWL, or you have representations of that data, you're in a better spot because you already have that in a semantic
Right,
form.
right.
One more question for that.
Sure.
Are you doing the training with that, or is it just a RAG with that, or you don't?
We're going to do the training with that, and then I'll show these practical design patterns, right? Because too much math, right? What can we actually do to improve our systems? So the cookbook here is to start small, start to build your ontology to describe the things that are going on in your domain, and focus on maybe 200 to 500 entities that fit the classes that you've described and 10 to 30 relationships between them. Now you have this input knowledge graph. You can do things like entity linking. So surface form tokens, are they the same? Are they close? Can we then link them together such that the language model can then just point to something in the knowledge graph and use that information? We can use it to add guardrails to an LLM. So if the output invalidates something that we know is true in our knowledge graph, we throw that answer away, or we re-prompt the LLM to give us a more correct answer. If you're going to be doing something like this, measure what matters. So do with and without evaluations on disambiguation data sets. So there's open data sets that you can use to train this, as well as do some common sense examples for clarity. So like the Jake Voracek example, I can go into that data set, I have that domain knowledge, I'm a fan of the team, I can see that these sentences are actually similar, whereas the training data set says they're not. And then iterate. Improve the ontology and knowledge graph, figure out what's missing, what other aliases do you need, did we design this with the wrong typing scheme, improve the graph, and you'll get improved LLM results. And what do I mean by improved LLM results? Well, we can look at one of them. So if I ask ChatGPT, given the two sentences, Jake with the assist and Voracek with the goal, on a scale of 0 to 5, how similar are they? Its prediction was 1. So I think we got, what was your prediction? 1? 3? 3 is good if you had that domain knowledge, which if we give that to the LLM, we provide a set of knowledge graph triples. Jake Voracek plays for Philadelphia Flyers. They're a hockey team. Goals and assists are on the stat line. How similar are these two sentences now? We get a 3 out of 5. So much closer alignment to the semantics that are being expressed in those two sentences. So all very theoretical work, right? Tons of math. But how does this actually work? Well, I've done it 3 times now. First, at a large US bank, as I mentioned before, we had this ontology and knowledge graph for personal and corporate entities. And different branches of the bank may maintain their separate databases. So mortgage may have a transactional database where they're aliasing these column names, and credit may have their own transactional database, and they may call those columns something different. So if we had to aggregate all of that information and run some query across the entire bank, that would be a mess if you wrote that SQL code. And if you tried to map one column name to the other column name by hand, that would just drive someone crazy. So what we did was we used this knowledge graph that we had, and we were actually able to come up with that mapping. And we could then use that mapping plus some natural language querying systems to ask those types of questions to our data. And this really helped enhance regulatory required reporting. To your question around healthcare, I worked for an animal health pharmaceuticals company where we did this. We had human health ontologies, so closer to the domain, but not exactly focused on animals. So what we did was we developed our own internal knowledge graph to reflect the information that we had. And we were better able then to match patents and publications externally to our internal research. So that improved our semantic search of molecular identifiers. In a more academic sense, we also applied this to metal organic frameworks, which are these crystalline structures in chemistry. And we're able to synthesize existing academic research via an LLM actually into a knowledge graph. We can use then those knowledge graph embeddings to predict crystal structures that might actually work out. So we verified these experimental frameworks prior to some PhD student going and cooking up a crystal in the lab.
I actually spent 2015 to 2018 working on building a clinical triple store on semantic web technologies at a major filter.
Awesome.
All based off of RDF triple stores and pure semantic web.
Yep. And that was kind of like the focus of my PhD was how do we marry these LLMs with semantic web? And then ChatGPT came out and everyone was like, semantic web's dead. It's not. That was, yeah.
Because 90% of your hallucinations in commercial AIs are because of the grounding.
You don't have that domains. Yeah.
Once you take this out, you're going to eliminate, if you bring in the skin with SNUMET, or any of the other existing ontologies and terminologies, you're going to eliminate 75–80% of
Those
the
mistakes.
statistical problems with that.
Right.
Right. Yeah, I'll repeat that just for the recording. There are existing domain-specific ontologies. So SNOMED is an important one in healthcare and human health. By having that extra domain knowledge, now your very general language model, if you pull one from the web or you're using ChatGPT, you can then remove the errors that come out of that model or the so-called hallucinations by feeding in that extra domain knowledge. So, summary of the talk in 3 sentences. We ground LLMs in factual knowledge using ontologies and knowledge graphs. We click language and graphs together such that we retain semantic meaning. And we can represent these knowledge graph triples as first-class objects to improve the performance of this machinery as well. And what you get out of it, fewer silly LLM mistakes, more consistent answers, better factual recall, reduced hallucinations, and better explainability and auditing as well. So with that, I will take questions, if there are any left. All right, that is it for me. Thanks.